good day. So our topic today is TCP, the second most important transport protocol. It's very widely used by many applications. So we will, and this is we have already discussed UDP. Actually, this is a little more complex than UDP, but it also has some advantages. So we will see what they are. So the transport layer responsibilities, if you remember, they create packets from byte stream received from the application layer, and they, in order to multiplex and demultiplex amongst various applications, it uses port numbers to create process to process communication. It uses a sliding window protocol to achieve flow control, and uses acknowledgement packet, timeout and retransmission to achieve error control. So you see, unlike UDP, which is unreliable, this seeks to provide a reliable communication. That means so that it is error free. It's a connection oriented protocol, as we will see, and it also has some kind of congestion control mechanism. We will discuss the details of that later. And of course, it does the basic thing of making connections between processes amongst two distant nodes possible. So TCP is called a connection oriented reliable transport protocol. It adds connection oriented and reliability features to the services of IP. So the IP as such, you know, is a best effort kind of service, so it does not give you any reliability. And secondly, IP is connectionless, whereas this is riding on IP, but this attempts to give some kind of connection oriented flavor to the connection. We will see how. And a proposer is implemented entirely at the ends, two end nodes. That means the internal, the intermediate routers, etc., they do not have any role to play. So the communication abstraction is that it is reliable, ordered. Ordered means that the packets are received in order. That means you remember that in IP it is not guaranteed that the packets will arrive in order, because what might happen is that one packet might be routed in one direction, the other packet might be routed in the other direction. So the packet which was sent earlier may land up at the destination earlier and vice versa. Okay. But TCP makes them ordered. TCP brings an order amongst them. So this is ordered, and this is of course point to point and unicast. And of these 2 points, that it is a point to point unicast and it is ordered and it is reliable, this is what gives the connection oriented flavor to TCP. And it takes a byte stream as an output and as an input and gives that as the output. Is the full duplex connection. That means both the nodes, suppose A and B are connected by TCP, so A can communicate to B and B can communicate to A, and it has flow and congestion control. So TCP, also known as transmission control protocol, it's a connection oriented protocol and it's reliable unicast end to end byte stream over an unreliable network. So before any data transfer, TCP establishes a connection. So just like you remember that, say, in a classical connection oriented network, like say classical telephones, first there is a connection which is set up, okay, by all kinds of control signal. Similarly, like say in ATM, first a connection is set up and then actual data transmission begins. Similarly, in TCP, a connection is set up between the two endpoints before any transmission takes place. So it sets up a connection. So one TCP entity is waiting for a connection, that is the server. The other TCP entity, the client, contacts the server. The actual procedure for setting up connection is more complex. So here this is just a very simple scheme. We will see the details of it, more details of it later on. So client first makes a request for a connection, and then so client makes a request, the server acknowledges the request and accepts the request, then data transfer begins. So there is a connection set up before actual data transfer can take place, and at the end of the data transfer there is a disconnect phase also. It's reliable. Well, the byte stream is broken up into chunks which are called segments. So, the TCP, they are called segments at the TCP level. So, receiver sends acknowledgements for segments. So, this is a basic mechanism by which reliability is brought in, that each and every segment is acknowledged. So, TCP maintains a timer. If an ACK is not received in time, the segment is retransmitted. So, this is the basic mechanism for reliability. So, the sender sends a packet and it is waiting, it waits for some acknowledgement. If the acknowledgement does not come through, the sender assumes that the packet has been lost and it sends the packet again. So, and naturally, so it is hoped that this packet will eventually reach the receiver and the receiver will send the acknowledgement. This might also lead to duplicate packets at the destination. For example, let us say the sender had sent a packet, the receiver received it and it sent an acknowledgement, but then the acknowledgement got lost. So, naturally the original sender did not receive any acknowledgement. So, after some time it will send it again. So, there will be a duplicate segment would be received by the receiver, but then it knows that it is a duplicate and can eliminate that. So, this way it achieves reliability. More about this later. And it can detect errors. TCP has checksums for header and data like UDP actually, and segments with invalid checksums are discarded. Each byte that is transmitted also has a sequence number. So, if some intermediate sequence number is missing, the receiver knows that something has been lost. So, to the lower layers, TCP handles data in blocks, the segment. So, this is where the packets actually originate, this is where the packet originate, but to the higher layer, TCP handles data as a sequence of bytes and does not identify boundaries between bytes. So, higher layers do not know about the beginning and end of segments. So, to the higher layer it is just a stream of bytes. So, let us say the application it writes 100 bytes, then it writes 20 bytes. So, all this goes into a queue. So, queues of bytes to be transmitted and then TCP transmits them. At the other end also there is a queue, and then the above application it reads, let us say 40 bytes at each go. So, so they do not, so these 100, so the to this application this is a byte stream, to this application also this is just a stream of bytes coming in such units. Now, more about the TCP segment. The unit of data transfer between devices using TCP is a segment. So, it is 20 to 60 bytes header followed by data. 20 byte header if there are no options, and up to 60 bytes if it contains some options. So, there can be up to 40 bytes of option. So, the header naturally contains some field which allows the TCP protocol to run. So, we will look into the details of this header. So, you have the header has a 16-bit port address, source port address, 16-bit destination port address, a sequence number, acknowledgement number, header length, reserved bits, some flags and then there are some options like window size, window size, checksum is already there. So, window size is there, checksum is there, and urgent pointer. So, that is 16-bit, and then there are options and padding. So, looking at them one by one, there is a source port address. You remember from our discussion about client server that processes actually communicate through ports, and the port and the IP address together form the socket which uniquely identifies every session. Now, when a TCP session is going on, so on both sides there are two port numbers are assigned. So, to start with, you remember that for standard applications the first communication will start on well known port numbers, then they will switch to ephemeral port numbers in case of concurrent servers. So, anyway, so there is a source port address which is a 16-bit address, defines the port number of the application program on the host that is sending the segment. Similarly, of course, there is a destination port address which is again 16 bits. So, port number as you remember that is up to from 1000 to 65,000, those are the ephemeral port numbers. So, it defines the port number of the application program on the host that is receiving the segment. And then there is a sequence number. This is a 32-bit sequence number. It defines the number assigned to the first byte of data contained in the segment. During connection establishment, a random number generator is used to create an initial sequence number, ISN. As you note that the sequence number, the field for the sequence number has been kept quite big, 32 actually, and that is with a reason. If the sequence number were very small, if the number of bits for the sequence number was small, then what could happen is that when a particular process session starts, so it is sending, and then it would go back to the beginning. So it would, naturally for any finite length sequence number, after some point, at some point it is going to go back. Now, if it goes back and starts these numbers once again for a very small segment size, what might happen is that first of all, two packets may get the same segment number which are on the network at the same time, and similarly other kinds of confusions might arise. So, what is done is that actually a large sequence number is generated, so that even if it comes back to a low number, we know that which one came earlier and which one came later. If after receiving some very high numbers you start getting some lower numbered sequence numbers, you know that it has looped back. Actually, this is not a strict loop, this is used as some kind of what is called a lollipop. Anyway, so even without going into the details, so this is this range of sequence number. So 32-bit of course gives you about 32, 2 to the power 32 is about 4 trillion, so which is a large number, and a random number is used to generate the initial sequence number. This initial sequence number, so that it's expected that in such a large range it is not going to clash the initial sequence number. So this ISN, and this ISN is exchanged between the two nodes. So about the details of the exchange we will see later. And then there is an acknowledgement number. Just as the segments which are being sent, they have a sequence number. Similarly, these segments, as they arrive on the other side, they will get acknowledged. So one acknowledgement after another will, so a stream of acknowledgements will come. Actually, in the best of circumstances, there will be as many acknowledged numbers as there are segments which are sent. So this acknowledged number will also start somewhere, and that would be communicated by the receiver to the sender in the connection setup phase. So that is also a large number, the 32-bit number. It defines the byte number that the receiver of the segment is expecting to receive from the other party. So this is the standard norm for the sliding window protocol. We have already discussed sliding window protocol earlier. We will just have a quick look for refreshing that later in this lecture. And the next field in the header is the header length, 4-bit. It indicates the number of 4-byte words in the TCP header. This is required because the header is of variable length. The header, as we have just noted, could be anything from 20 bytes to 60 bytes depending on the options. So the header length is to be specified, and then there are some reserved bits for future use, followed by some pointers, followed by some flags. So there are defined 6 control flags, ERG for urgent pointer, whether the urgent pointer, whatever is there in the urgent pointer field, whether it is valid or not. So this has to be set. If the urgent pointer is not valid, the urgent pointer field itself may contain some garbage. Acknowledgement is valid or not. PSH is request for push. RST is for resetting the connection. SYN, the synchronize the sequence number. and fin to terminate the connections. These flags are used for setting up and termination of connections. We will come back to these later on. Then there is a window size 16-bit. It defines the size of the window in bytes that the other party must maintain, okay, and it is sort of controlled by the receiver. So the receiver gives the window size. This window is of the sliding window protocol, and then there is a checksum which is 16 bits. It contains the checksum. The checksum is just like UDP. The urgent pointer is 16 bits, valid only if the urgent flag is set. It defines the number to be added to the sequence number to determine the last urgent byte in the data section of the segment. And options is up to 40 bytes. Option could be single byte or multiple bytes, and it may contain maximum segment size, window scale factor, timestamp, etc. if it is multiple bytes, or it just simply shows as in a single byte the end of options and no operation for padding purpose. So, end of option is used for padding at the end of the option fill, and no operation used as a filler between the option. If there are options, on the other hand, one option is maximum segment size, defines the size of the biggest chunk of data that can be received by the destination of the TCP segment. This is the size of the size of data, not the segment. So, which is I mean taking the header field out. Window scale factor defines the size of the sliding window and how it is to be changed. More about changing window sizes later on. And timestamp filled by source when segment leaves and destination returns it in the echo reply field. This allows the source to determine the round trip time. This round trip time, some estimation about the round trip time is very essential, because once suppose, I mean if we are just talking about the error control through acknowledgement, suppose a particular segment has been sent. Now it is now the sender is expecting an acknowledgement. So, if the acknowledgement does not arrive, but the question is the acknowledgement does not arrive by what time? Okay. How long would the sender wait for the acknowledgement to come? So, you have to make an estimate, and that estimate is based on the round trip delay. Okay. So, maximum segment life. So twice that. So, that much it has to wait, maybe some more, and only then the sender would sort of come to the conclusion that maybe that original packet is lost, or maybe even the acknowledgement is lost, but in either case the packet or the segment that was sent, it has to be retransmitted. Then there is the checksum. As I said, the same calculation as UDP. Inclusion is of course mandatory with TCP. Now about setting up connections and resetting of connections. TCP is a connection oriented protocol. So, a connection, that means a virtual path between the source and the destination, has to be established. This is only a virtual path, because once again remember that TCP is working on IP, that means an IP is a connectionless service. So, the underlying actual service is actually connectionless, but TCP gives the sense or gives the feeling to the upper layer, meaning the application layer, that as if it is a connection oriented thing. That means all the good things about connection orientation, like segments arriving in order and they are reliable, etc., that is present. But TCP has to work on a connectionless IP network. So, this path that is set up, path that is established from the source to destination, this is only a virtual path, unlike traditional strict connection oriented service where the connection may be physical. Now, for connection establishment, 4 actions are required before sending data. So, and actually this is 4 actions, but 2 of them may be combined. So, it is maybe a 3 actions also. We will see what they are. First, host A sends a segment. Suppose host A is the client which is sort of trying to establish a connection to a server, maybe say host P. So, host A sends a segment to announce its wish for connection and includes its initialization information. Okay. And then host B sends a segment to acknowledge the request of A. So, host B sends back an acknowledgement. Then host B sends a segment that includes the initialization information. So, what you might do is that the second and third step can be combined. That means, the host B can acknowledge the request of A, as well as in the same acknowledgement it might send a some initialization information, meaning the sequence number, etc., they have to be exchanged. Then host A sends a segment to acknowledge the request from B. Second and third can be combined. This is called three-way handshaking. So, the first SYN, that means for synchronization, that is the sender sends a synchronization, that is the request to set up a connection to the host, and it also gives its initial sequence number. The receiver then sends a SYN, its own SYN, that means it sends its own sequence number, which is something like 4800 here, and an acknowledgement of 1200. So, this segment which is coming, which is the segment 1, already consumes the first sequence number 1200. So, it while acknowledging, it sends the value 1201, meaning that 1201 is the next segment, or the next segment number that the receiver is expecting. Of course, what might happen is that this packet may get lost, because once again the TCP is sitting on a best effort kind of IP service. So, it may get lost. So, what will happen to the sender is that sender will not get any acknowledgement. So, after some time it will send the SYN pack again, I mean if it is persistent, and then finally it will get the SYN and the acknowledgement. Similarly, if this is lost, once again this is sent after some time, so that finally this is achieved, and then the sender sends the sequence number now 1201 and acknowledgement 4801. So, you see this sequence number is always the next number that is expected from the other side. When it sent 1200, sequence number 1200, it replied back saying that it is next expecting 1201, and its starting number is 4800. So, he replies in his acknowledgement that the next acknowledgement he expecting is 4801. So, this way. So, this is the three-way handshake where the SYN and the ACK has been combined, and the data transmission can start. And on the other side, we have to think about the connection termination. Either party of course can close the connection. If connection is terminated in one direction, data can continue to be sent in the other direction. Remember that this is a full duplex communication. That means A is communicating to B and B is communicating to A at the same time. Okay. Even if only predominantly one side is sending data to the other side, but anyway the acknowledgement is coming from the other side anyway. Now, the connection can be terminated from both sides, but then somebody has to initialize the termination. So, if connection terminated in one direction, data can continue to be sent in the other direction. So, 4 actions are required to close the connection in both directions. Suppose both directions the connection now has to be closed. First, host A sends a segment announcing connection termination. So, which means that it sends a segment containing FIN. You remember all the SYN, FIN, etc., those are the flags in the segment in the header. Host B sends a segment acknowledging the request from A. After this, the connection is closed in one direction. When host B has finished sending data, sends a segment indicating connection closure. Okay. These two, for example, that second step and the third step, they cannot be combined together, because although we are sort of allowing the termination of connection from one side, but from the other side he may have acknowledgements or other things to send to this side. Okay. So, he will not terminate the connection. So, these two cannot be combined together. The third step can be taken only when host B has finished sending data from its side and it sends a segment indicating a connection closure. Host A acknowledges the request from B. So, this is called a four-way handshaking, and this is the this is a diagram showing a four-way handshaking. For example, assume that the sender has sent a fin in a segment 2500, and when it receives the fin, if everything is all right, he will send back an ACK, and he will say of course that the next one that he is expecting from the other side is 2501, sequence number 2501, and sequence 7000, which is the acknowledgement for this fin. After some time, when B is finished sending all its acknowledgements or other things that it might want to send to sender, then it sends a fin from this side. So, this is for closing the connection from the other side. The acknowledgement that is expected once again is 2501, because this is still 2501, because nothing else has arrived from the other side. So, it is still 2501, and the next it takes the next segment number 7001 from this side, and he acknowledges this second fin, and this when the acknowledgement reaches here. So, everything is closed gracefully. Of course, things may not run so well because some or more one or more of these packets may get lost on the way, because we know that the underlying network is unreliable. If the first fin is missed, of course, he does not get any acknowledgement. So, after some time he will send a fin again. If similarly, if this ACK is not received, but then he will send this fin once again anyway. So, this fin this fin again may be lost. So, since he does not get the acknowledgement, he will send a fin after some time. The trouble is over here, because you see at this point of time, after sending this acknowledgement, the sender will assume that everything is fine. So, he will close, but this last acknowledgement may get lost. So, you cannot really, and now once this side closes, because he sees that all the fins have been sent and received and the acknowledgement has been received and sent, so he will say that that is the end of the story. But for him that is not the end of the story, because this ACK is now lost. But if this fellow has already completed, he will not send any ACK any longer. So, what he will have to do is that after some time he will have to close the connection anyway. Actually, the TCP goes through some through a state diagram. This is the state diagram, and these are the different states. So, let us just quickly look at this. So, state and the description. One is of course closed, that means no connection is active or pending. The other is listening, maybe the server is waiting for an incoming call. SYN received, that somebody has made a request, a connection request has arrived, wait for acknowledgement. SYN sent, the client has started to open a connection, that is from the client side. Established, that means the connection has been established and normal data transfer state, and that is the normal data transfer state. Now, while finishing, fin wait 1, this is the client has said that it is finished, and fin wait 2, that is the server has agreed to release. So, that is the state, and timed wait, wait for pending packets. This is, as I said, the 2MSL wait state. So, for the last pending packet to come in, you have to wait at least this much, and this is the maximum segment life. This is sort of estimated from the round trip time. Closing, both sides have tried to close simultaneously, and that is again another. So, both sides have sent fin and close a wait. Server has initiated a release and last act waiting for the pending packets. So, when it is closed, of course, nothing is happening. Now, some SYN or SYN plus ACK it receives. So, once it receives that, it goes to the SYN received state, and then this way. So, as we have explained earlier, this is the connection setup phase, and once the connection is set up, it reaches the established phase, and then the two-way communication is going on. Then after this, it may sort of go through the closure, either through the closing and then fin wait 1, fin wait 2, time wait. So, let us not go into the details of this part, and here the close wait and the last act. So, this is very roughly the state diagram of TCP. Let us just look now a little bit into the flow control that is implemented by TCP. So, this defines the amount of data a source can send before receiving an acknowledgement from the destination. TCP uses a window imposed on the buffer of data to limit the amount of data sent before an acknowledgement must be received. So, this is the traditional sliding window protocol, which we had discussed while discussing the data link layer. So, we will just go through this very quickly now. So, in the sliding window protocol, a sliding window is used to make transmission more efficient as well as to control the flow of data, so that the destination does not become overwhelmed with data. So, what is done is that, suppose this is the occupied part of the buffer, and out of this a number of packets or segments have been sent, but they have not been acknowledged, and these are the next byte to be sent. This is what is there in the buffer. Now, depending on the window size, now say the buffer contains so much. Now, depending on the window size, it can go on sending these bytes, or if the window size is already over, then it has to wait here. So, this is sent and acknowledgement and sent and acknowledged. Suppose nothing has been acknowledged as yet, and let us assume that the size of the window is 3 units. In that case, the sender has to wait here till some acknowledgement comes, and if the acknowledgement comes, suppose 200 is acknowledged, then the window will automatically slide, and this now can be sent. So, on the other part also, he is receiving he has received 194 etc. So, these have been received. So, this is the occupied part of the buffer, and from this buffer the destination process will keep on consuming the data from these segments as a stream of bytes going out of this segment, and this is the empty part of the buffer where new segments can come in. So, suppose the size of the receiver window is this much, let us say size is 7. So, after having sent this, the sender can go on sending up to the receiver window size. The point is that if it is if a window size is not fixed, what the sender might do is that the sender may send in a lot of packets, or maybe the channel is absolutely bad. in that case none of the packets have received on the has gone to the other side, and so you will have to send all these packets once again. That is one point. And secondly, the sender may be very fast, but the network may be congested. So the sender will push in a lot of data, but that will only make the congestion worse, and so whatever would have received on the other side, now that does not reach the other side because the intervening network has been congested, maybe some buffer has overflowed, some router has dropped some packets, etc. So there is a limit on the window size. Of course, the window size also has a bearing on the speed at which effective data transfer is taking place. If the window size is very small, then after sending, suppose the window size is only 2. So after sending 2 segments, the sender has to wait till the acknowledgement comes back. So the efficiency of the channel goes down, because for each acknowledgement, of course, the packet will reach the other side, and then the acknowledgement will travel all the way back. So it is a round trip delay. So suppose the window size is only 1. So after sending each segment or each byte, you wait for the round trip time and then you send the next byte. So that becomes, now the overhead has become very high. Of course, this is the minimum possible rate at which the sender is sending. On the other hand, if this window is very large, a large amount can be sent even without waiting for acknowledgement, and everything is fine. So the stream of acknowledgements will also come start coming in after this round trip delay, and the overall efficiency would be high. So between the congestion and the efficiency at which data can be transferred, the data transfer speed, the effective data transfer speed, so there is a trade off. So the details of the sliding window, we have discussed sliding window protocol earlier, so I will not go into the other details of the sliding window. So as the acknowledgements are received, the window slides, and as data is received, now this is the point. Suppose these are the sequence number. Now suppose in the receiver side, maybe say 205 has got dropped somewhere, 206, 207, 208, 209, etc. has come. So after acknowledging 204, where he will, in the acknowledgement packet, he will say that the next byte I am waiting for is 205. Although 206, 7, 8, 9, etc. have been received, but he will not send any acknowledgement. So after some time, the sender will sort of realize that the next this acknowledgement for 205 has not come. So he will start pumping this 205, 6, 7, 8, 9 again. As soon as, suppose the next 205 actually arrives. So as soon as 205 arrives, what happens is that this gap is closed, and it will, the window will slide all the way here, and he will say that the next byte that is expected is 210. And then what will happen is the 206, 7, 8, 9 now becomes duplicated segments on the receiver side, so they are simply dropped. So using these segment numbers, not only we can put them in order, suppose 206 has come earlier, 205 has come but has come later, but then they can be put in the proper sequence because the sequence number is there, that is one thing. And secondly, even if this 205 was lost, it can still be recovered by this retransmission, etc. So that is how this protocol is reliable. And of course, when this is acknowledged, the window slides. So this is the size of the receiving window. So this way, and what sometimes what happens is that, and we will discuss the details of this later on, if there is actual congestion in the network, that you will find out only after sending some packets and then seeing that some acknowledgements are not coming and the packets have got lost. So what the sender then the conclusion that the sender draws from not receiving acknowledgement, etc. One thing is, of course, this packet may have got lost. That is one thing. And secondly, lost why? Maybe that the network is congested. So what will happen is that there is a mechanism for automatically reducing the window size, so that now you are going to transfer data at a much lower rate, but then you are sort of trying to control the congestion. So this is the congestion control that is inbuilt into TCP. There are some variations as to how this window size is going to be changed over time, etc. So we will come to that later on when we talk in more details about congestion control. So in TCP, the sender window size is totally controlled by the receiver window value, the number of empty locations in the receiver buffer. However, the actual window size can be smaller if there is congestion in the network. So the source does not have to send a full window's worth of data. That means suppose you do not have so much data to send, naturally you would send less. The size of the window can be increased or decreased by the destination. The destination can send an acknowledgement at any time. Now little bit about error control in TCP. TCP, you know that it has to be reliable transport protocol. So TCP tries to deliver the entire stream to the application program on the other end in order, without error and without any part lost or duplicated. So TCP provides reliability using error control. So for error control, these are the different things that TCP would do. It detects corrupt segments by detecting lost segments, by detecting out of order segments, by detecting duplicated segments, and by correcting errors after they are detected. Detecting corrupted segments, how do you detect corrupt segments? Of course, your checksum would be wrong. So in that case you can maybe drop it, or if you can correct the error using the checksum, then maybe you will correct it also. Detecting lost segments, this is achieved by getting the with the help of the sequence number. So we have the sequence numbers, and if one particular segment in between is lost, we know that this segment number is lost by because that that particular segment number would be missing. Detecting out of order segments, well, if the segments are come out of order, since we have got the sequence number, we can put them in order. We can detect it and correct it, of course, at the same time. And detecting duplicated segments, if a particular segment has come twice, maybe its acknowledgement got lost or delayed. In that case, once again using the by the serial number, we can see that it is duplicated and we can drop it. So error detection is achieving using these three simple tools: checksum, acknowledgement, and timeout. Because sometimes an error, for detecting an error, because suppose you had sent the first segment and acknowledgement never came. So after some time you have to give a timeout, and that is how the sender detects that this segment has been lost and it has to be retransmitted. So the checksum, acknowledgement, and timeout, these three things together gives the reliability and error detection capability of detection and correction capability of TCP. For error correction, when timeout counter expires, segment is considered to be corrupted or lost, and the segment is retransmitted. Now about the TCP timers. So TCP has to maintain a number of timers inside, alright. So that software, so actually TCP has to do a lot of work to give the reliability which is necessary on this unreliable IP service. So that is why this protocol is a little more complex than others, but then at the same time this is necessary, For example, when you are sending, let us say, a file transfer protocol, for example, you are transferring a file from one machine, one distant machine to the other. Okay. Even the misplacing of a few bits may make the whole file useless. So, it is important. So, there are applications and specifically say protocols like FTP and HTTP, etc., they use the TCP protocol because there the reliability of the connection and error control, that means absolute error free nature of the communication is very vital. Then there may be applications where a few bits or bytes lost here and there really does not matter. For example, suppose we are carrying a voice communication. Now, if you are carrying voice communication, what would happen is that even if it is found that even if a few bits here and there are lost, the quality is not impaired that much. Of course, it is voice or other multimedia kind of communication is very sensitive to other kinds of network parameters, and we will come to that later on. But anyway, the point is that even if a few bits are lost here and there, the voice communication, the other person will also be able to make out. So, in this case, on the other hand, if there is delay and that means differing rate of transmission, because if the window size is large, you know that the rate at which you can transmit is high. If the window size is small, the rate at which it can transmit is small. So, if the rate at which transmission is taking place, if that keeps on varying or it takes a lot of time, etc., that is not acceptable for say a voice communication. So, those are cases where we will not use TCP. So, there are cases where we definitely want to use TCP because of its reliability, and then there are cases where we do not want to use TCP. Okay. So, FTP, HTTP, etc., these are examples where TCP is necessary and we use them. So, TCP uses 4 timers: retransmission timer, persistence timer, keep alive timer, time weighted timer. First is, let us say, this retransmission timer. This is used to control a lost or discarded segment. Suppose some segment is lost. Now, after what time will it be retransmitted? So, this retransmission timer, so in using the timestamp you can get an idea of the round trip delay, and this you will use to set your retransmission timer. So, after this after that of course you will give some buffer because it is never constant. So, so that this way you can set up your retransmission timer. As soon as a segment is sent, immediately a retransmission timer starts. Okay. Of course, when the next segment is also sent, because your window size happen to be more than 1, you will need another retransmission timer for this segment. So, for each segment we are maintaining this retransmission timer, and as soon as this one of these timers is times out, that means that packet was sent and the acknowledgement was not received, immediately you have to retransmit that packet. So, this is the retransmission timer. TCP creates a retransmission timer when it sends a segment. If an acknowledgement is received before the timer goes off, the timer is destroyed, because this timer is not required. For other segments, of course, for each new segment you start a retransmission timer anew. If the timer goes off before the acknowledgement arrives, that means the acknowledgement has not arrived within estimated or hoped for time. The segment is retransmitted and the timer is reset. Now, this timer will be reset, because after, even though you retransmit, the retransmitted segment may also get lost. So, you have to start the retransmission timer anyway once again. And so, TCP uses a dynamic retransmission time which is different for each connection and may be changed during the connection. The point is of course, you have to understand. So, the TCP is a protocol and there may be a lot of connections going through this TCP protocol. Just think of a simple case of a web server. Now, there may be a number of people for very active websites, a number of people may be hitting it almost at the same time, alright. So, if you have a concurrent server, you have spawned so many processes on the application side, and each of the server is sort of serving one particular client and a number of them. So, a number of TCP services are going on at the same time. Of course, they are using different port numbers. So, whenever any acknowledgement or anything comes, you will see the port number to determine which process to which process this belongs to. That is one thing. But secondly, now assume, now just think of two clients who are using the same server at the same time. Now, the two clients may be connected in, of course, they are, I mean, most probably maybe in two different networks, and the round trip time for each of these clients may be different, alright. Since the round trip time is different, so you cannot use the same kind of retransmission timer time for each of the connection. This has to be dynamically assessed from the timestamp. So, it may be different for each connection and may be changed during the connection. Then there is a persistence timer. What might happen is that when a TCP receives an acknowledgement with a window size of 0, it starts a persistence timer. Now, what does a window size of 0 mean? Window size of 0 means now that please do not send anything at the moment, okay, because either I am overwhelmed or something is sort of wrong in between. So, anyway, it is very congested, so please do not send anything. So, what would the sender do? He will start a persistence timer, and when the persistence timer goes off, the sending TCP sends a special segment called a probe. So, now before trying to send anything, because you remember that what may have happened is that his buffer may have become full. So, now you have to find out, before sending a packet, you have to find out whether he has recovered. So, you send a probe segment. So, this is a special segment which is also used in we will come to that keep alive timer. So, it sends a probe segment. So, this prevents a deadlock from occurring in case that an acknowledgement is lost. Anyway. And then there is a keep alive timer, prevents long idle connections between two TCPs. Suppose the two sides their connection has been set up, nobody has closed the connection, but both sides are idle for a long time. Now, after the keep alive timer goes off, that means after that, so as soon as the TCP connection is set up and some communication, after the last communication, this keep alive timer is automatically started. And when you see when the keep alive timer goes off, that means there has not been any communication between the two for a long time. Now, what has happened? What might have happened is that the other side might have switched off and gone home. Forget about any TCP, all right. So, it might have happened. So, you have to, so the other side has to find out. So, it is not that always there is a graceful connection, I mean severing of connection between the two sides. So, it may not happen. So, you send a each time the server hears from a client, it resets the timer. Okay, the other side is alive, so it resets the timer. So, it starts from the counting down from the beginning. If it does not hear from the client after the timer times out, it once again sends a probe segment to see whether the other side is alive or not. If the other side is indeed alive and wants to keep the connection on, so he will reply to the probe segment, and then he will know that okay, he still wants to do something, but it is just that he is very preoccupied at the moment and will not that is why he is not sending. So, this is the keep alive timer. If on the other hand he has switched off and gone home, this probe will go unanswered. So, after some time this side will take some action to close everything. And time weighted timer used during connection termination. when TCP closes a connection, it is not really closed until this timer times out, allows for fin segments to be received. You remember that last case where the last acknowledgement has not been received, okay, because it got lost. So everything was fine, but the other side has actually gracefully terminated the condition and stopped it. So he has to wait for some time, and he has to wait for a time which is more than twice the round trip delay. That is so this is called, so it waits for this time weighted timer, and once that is over, then the segment can be then the TCP connection can be terminated. Okay, with this we close our discussion on TCP, and there is some more variants of TCP regarding how you control the window sizes, etc. So we will discuss it when we discuss congestion control. Thank you.